So this should give you strong like Algebra 1 vibes from back when we were given 2 points and you had to find a line that passed through them. It's similar to that, except we're trying to put it into an exponential function now. So as a reminder, an exponential function is in this form: y equals a times b raised to the x. So our difficulty today is that we're going to have to solve for 2 variables at the same time, a and b. So part A, we want to find the graph, the exponential function of the graph that passes through the points 1, 12 and 3, 108. So there's going to be basically 4 steps here. Our first step is that you're going to substitute points into y equals a times b to the x. So we're going to do that at the same time with these 2 points. So from our first point, we'll have 12 equals a times b to the first. For our second point, we'll have 108 equals a times b to the third. Okay, so how we're going to solve for our variables. We're going to solve for b first, sort of. So we want to, solve for a first. Solve for a in first equation. Oh yeah. Solve for a in first equation, then plug into second. So we're just going to rearrange that first equation, and we're going to plug that a into our second equation. So up top, remember a, we had 12 equals a times b, so we're just going to divide both sides by b, and that will let us solve for a. So we have a equals 12 over b to the first, or just b. We'll take that, and we're going to plug that into this 108 equals, but instead of a, we have 12 over b times b to the third. So now we want to just simplify and solve for b. So I should say can solve. So when you simplify this, this is the same as 108 equals 12b to the third over b. If you apply your exponent properties here, go sideways so you don't have room here. This is the same as 108 equals 12b to the second. If you divide both sides by 12, you get 9 equals b to the second. Take the third root of both sides. I'm sorry, not third root, second root. And you're going to get that b is equal to 3. Now for my quick math students who are like, hey, isn't it b equals plus or minus 3? You're still right, it is technically plus or minus 3. However, exponential functions can't have negative b's, so we're just going to throw out the negative. So we're just only ever going to worry about the positive, and you don't have to worry about plus or minus or anything like that. So we have solved for b. So now we need to solve for a. So that's kind of our third step here. We're going to plug b into the a equation and solve. So our a equation was this one up here, this a equals 12 over b. So we have a equals 12 over 3. So we end up with a equals 4. Right, now we've got both of our a and b, so we're good to plug this into the general equation. So fourth step, plug a and b into y equals a times b to the x. So we have y equals 4 times 3 to the x. And that's it. A lot of work to get that little equation, but there it is. If you remember from Algebra 1, it was always a lot of work finding these equations, given 2 points, and plug things back and forth, just because you're solving for multiple variables. One note here is Go Formative, that dot is not readily accessible. So to get the dot on Go Formative, so to get dot on Go Formative, there's 2 ways you can do it. If you like computer language, like some coding stuff, the way you can get it for that one is that you type \c dot and hit space and it turns into that dot. Or, we talked this last hour, you can just hit the asterisk and it turns into that. I'm also fine if you use the times button that's in the Go Formative.
So you can keep it as that and not do 12 to the x?
No, because 12 to the x would be breaking x, or order of operations, right? The x is only on the x. Good question. Yeah, John.
Under example 2, when you multiply the fraction by b cubed, how come they only went to the top?
Because if it was going to the bottom, then you're multiplying by b cubed over b cubed, which is a different number. That's like multiplying it by 1. Anytime b cubed is the same as b cubed over 1, right? So you multiply straight across. Yeah, Mike?
Do we just pick in the first thing, is the 12 and the 108, do we choose those if they're the y?
Yes.
Okay,
Yeah, this
okay,
is
I
your,
get it now.
that's your x, that's your y.
Okay, I got it.
And technically, we could have solved for a from our second equation, but then we have a b cubed. It doesn't really matter the order you do it, but generally it's easiest to pick the one that has, a 1. You will on your homework have a few that aren't those nice exponents. Like I think one has a negative 1, so that gets into around the next one. We'll do it. Let's look at another example and see if that clears up any other questions, because it is just part of the process. So part B, we have 1, 10, and 4, 80. So again, our step 1 is to sub points into y equals a times b to the x. So we're going to do this 2 times. We have x, y, x, and y. So this first one will be 10 equals a times b to the first. My second one will be 80 equals a times b to the fourth. First step, sub points into y equals a times b to the x. So we have 10 equals a times b to the first, and 80 equals a times b to the fourth. Alright, so our second step is to solve for a in first equation, first sub into second, and solve. So we're going to rearrange this first equation here, divide both sides by b. So you'll have a equals 10 over b. In this case, it's b to the first. I think on one of your homework ones, it's b to the negative 1. So when you sub that into your second equation, you'll have 80 equals 10 over b times b to the 4th. And then to Josh's last question, it's really b to the 4th over 1, so that's why we multiply straight across. So this is going to be 80 equals 10 b to the 4th over b, which just simplifies to be 80 equals 10 b to the 3rd. Divide both sides 8 equals e to the third. Here we have to take a third root, not the square root. So we should get b equals 2. We're worried about plus or minus here, so it's easy anyway. The cube root of 8 is 2. Yay, we found b. Now we just have to find a and put it all in. So our third step here, plug b into equation, and solve. So a was equal to 10 over b, and instead of b, we're going to put 10 over 2. So we get that a is equal to 5. So our last step, plug a and b into y equals a times b to the x. So now we leave our y and our x alone. We just plug in a and b. So we'll have y equals 5 times 2. All right, quite the process. Any questions about it? So lots of steps here to remember, but essentially you're just solving for a, and then you plug it into your equation to solve for b, and then you plug that back in to solve for a as an actual number, and then you plug those into that general equation. So lots of back and forth, which is always what happens when you're just given 2 points and you're supposed to find the equation. Alright, so why are we talking about exponential functions after coming off of talking about logarithms for forever? Well, it's because of this second box down here. And a few of you might have noticed this as you went through the optional alternative assessment. This is actually one of the more applicable things we talk about in Algebra 2, and it's this idea of transforming exponential data. So a set of more than 2 points xy fits an exponential pattern if and only if the set of transformed points x, comma, natural log of y fits a linear pattern. So what some very smart people figured out is that when you have these exponential graphs, when you have data that grows exponentially, you can actually switch it down into a linear model using this idea that you convert all of your y's into the natural log of y's. This is what they do for pH. This is what they do for the Richter scale. This is how it just lets you represent the data in a way that's more visually, it makes sense more. And again, that's because once you get to high values here of y, relatively low values of x, your y's are way up here. And once you're to the point where it looks almost vertical, it's really hard to interpret the data. So that's why they do this. And it's actually a pretty decent process for us to do. The one thing I want to remind you of is, if you remember from Algebra 1, you have this equation y minus y1 equals m times x minus x1. And this is an equation for a linear line, because again, we're talking about a linear line. You had to use this when you were given a point and a slope, or if you were given 2 points, you had to use this. Probably the least favorite of the forms. No, that's not true. Standard forms. But this one is one that you guys definitely worked with in Algebra 1. We're going to be using this again with one slight modification, because we are talking about linear functions, but we're talking about them when they switch down exponentials. So we're going to talk about it when it's natural log of y minus y1 equals our slope times x minus x1. This is going to let us find that line. So as a reminder too, m, remember, is your y2 minus y1 over x2 minus x1. So we're going to be finding this line given from 2 points. Now, the last thing to note here is that some data doesn't perfectly fit this linear model. So you'll have some exponential data where once you squish it down to a linear, not all of the points are on this line of best fit, as we call it. So that's one way to measure if the data truly is exponential in the first place. So example 2 here says a store sells motor scooters. The table shows the number of Y scooters sold during the X year that the store has been open. Part A wants us to draw a scatter plot of the data pairs X natural log of Y. And then it wants us to determine, is an exponential model a good fit for the original data pairs X, Y? So what we're asking ourselves is, once we plot these points, do they make a good linear line? Is it pretty close? It's not clear to tell. I mean, it's pretty clear right away if we look at these numbers. This is not linear. These are not changing by the same amount. But the question is it truly exponential? That's a little harder to tell. So your first step here is that you're going to be given either a table or a series of points that are just the normal ones. So our Y, our X is our years, and Y is our number of scooters sold. We want to convert this into this X common natural log of Y. So to do this, in our table, if you look at 1, that's with 12. So for our table here, you're going to do natural log of 12, which if you plug that into your calculator, you should get 2.48. For 2, we're at 16, so you're going to do the natural log of 16, which is 2.77. At 3, we're at 25, so it's the natural log of 25, which is 3.22. At 4, we're at 36, so it's the natural log of 36, which is 3.58. At 5, we're at 50, so it's the natural log of 50, which would be 3.91. At 6, we're at the natural log of 67, which will be 4.2, 0. And at 7, we're at 96, so we the natural log of 96, which is 4.56. So in general, we're rounding to the second decimal place here. All right, we're back to graphing. For these ones, it's really important that we're labeling our axes, and we are not counting by 1. So do not try and pull counting by 1, because I'm not going to like that. We have to count by something different. So first of all, this is our x-axis, and this is the natural log of y. Probably one of the first times we haven't labeled it as y. You're going to have to play with these a little bit to see which what best fits this. I need to go up to 7 on my x-axis. So if we skip 3 boxes, this lets us count up to 7. So we have 1, 2, 3, 4, 5, 6, and 7. We need to be labeling our axes, and we are not counting by 1. I mean, we are counting by 1, but we're not skipping, or we're not just counting 3 boxes.
Why can't we do that on the x-axis? I mean, on the y, it's kind of hard, but why can't we count by 1 on the x?
It's just because it makes everything look really squished. Yeah, I mean, so technically you could count by that, but if we're going to be spreading things out anyways, if you're only going to 7, you can watch that. If you did count by 1 on the x-axis, you're right. You're fine with that, but if you do it on the y-axis, that's just good. So, for the y-axis, my favorite things to count by are either 0.25 or 0.5. If you can get away with those two, that's perfect. In this case, 0.25 works really well, because counting by 25 is actually pretty easy for us, because we have quarters. So we're used to those. So if you skip 4 boxes here, this is 1, 1.25, 1.5, 1.75, 2, 2.25, 2.5, 2.75, 3, 3.25, 3.5, 3.75, 4, 4.25, 4.5, 4.75, 5. So that's my personal favorite to count by. It's generally pretty easy, gives us a good spread, and we can fit it. So let's plot these points. At 1, we should be at 2.48. So 1, go just below 2.5, and we are 2.48. At 2, we'll be at 2.77, so just above 2.75. At 3, we're at 3.22, so just below 3.25. At 4, we're at 3.58, so just above 3.5. At 5, we're at 3.9, so just below 4. At 6, we're at 4.2, so just below 4.25. And then at 7, we're at 4.56, so just above 4.5. Pretty linear. We're going to draw our line of best fit. So I generally grab like the last point or the first point, and then I'm just going to draw a line like this here as nicely as possible. So you can see this isn't perfect, and it's not meant to be perfect. It's sort of an estimate here. But most of the points are really close. This would be a good line of best fit. So basically what we conclude is that really this is an exponential model. These numbers are exponential, so we are able to squish it down into a linear using this exponential regression. Any questions about the graph? Again, on GoFormAt, I know it's a little touchy, so if you want to graph it in Notability and then just insert that picture into GoFormAt and find that, I think we'll do that. It's very nice. Alright, so we want to find an exponential model for the original data. Here is where it's a little tricky. I'm going to show you how to do this by hand, and then we're going to talk about how to do it in calculators. So, we're going to do it by hand, hopefully only one time, and then you'll have a calculator, and if you forget your calculator on a test, I'll tell you to do it by hand. We've got it. So open your calculator. So we want to find an exponential model for this original data. So again, we're going to be using this natural log of y minus y1 equals our slope times x minus x1. Our first step here needs to be that we find our slope. So find m using 2 points. Alright, so that last part of the sentence, where I say use 2 points, that's a little tricky too, because depending on your 2 points, you're going to get a different slope. So if you chose point 1 and 2, and I choose point 1 and 7, we're going to have different slopes, meaning we're going to have a different final answer. They'll be close, but they'll be different. So this is one of the downsides of doing this by hand, is that we're just arbitrarily choosing points. In general, what you want to do is you want to choose 2 points that are actually on the line. So I'm choosing the first point and the last point because they're actually on the line. I drew it that way. You want to choose 2 points that are on the line. So I wouldn't want to choose this point because it's pretty far off. But again, this is sort of your discretion, so answers might be a little different. Not too different, though. So I'm using 1, 2.48, and I'm using 7, 4.56. I love to name my points, so this is x1, y1, this is x2, y2. So my slope here will be m equals y2, so 4.56 minus y1, which is 2.48, over x2, which is 7, minus x1, which is 1. You enter this into your calculator, you're going to get that this is about 3.5. For these, in general, round to the second decimal place for everything. Okay, I found my slope. One thing I need. My second step now is going to be to find the equation. So I'm going to plug x1, y1, and m into natural log of y minus y1 equals m times x minus x1, and solve. The solving part is a bit of so we're plugging in, again, we're plugging in here, here, and here. So I'll have the natural log of y minus my y1, 2.48, equals 0.35 times x minus 1. I should add in solve for y. That's specifically what I'm solving for. So I need to get that natural log of y by itself because I'm going to need to exponentiate both sides, right? I'm going to use C to E to both sides. All right, the journey begins. Let's start by multiplying that 0.35 into this parenthesis. So we have the natural log of y minus 2.48 equals 0.35x minus 0.35. I can then add 2.48 to both sides. So I have the natural log of y equals 0.35x plus, this is 2.1. So I have natural log of y equals 0.35x plus 2.13. Good stuff. I'm going to take b to both sides now. I'm going to exponentiate to get rid of that natural log. So when I do that to the left side, that's just going to leave me with an e times r y. On the right side, I have e raised to this whole thing. It's 0.35x plus 2.13. Here's where the book has a lot of faith in us. We have gone the other direction. We have never gone in this direction. So what I mean by that is, if you look at this plus, using our exponent rules, right, we can split this up. We've always done, if you have two exponents being multiplied, you add their powers. Now this is saying we're adding our powers, so let's split our exponent into two exponents being multiplied. So we have y equals e, and then I'm going to switch my order here too, so it's in standard form. E to the 2.13 times e to the 0.35x. And then we're going to pull the same maneuver. This 0.35x is the same as 0.35 times x. We only multiply x when we raise a power to a power. So we have y equals e to the 2.13 times e to the 0.35 raised to the x. Now the reason we did that is because you can plug in e to the 2.13 in your calculator, and you can plug in e to the 0.35, and you can get actual numbers. We want actual numbers. So when you do that, you'll get y equals 8.41 times 1.42 raised to the x. That is our exponential model for this scooter sold. So that means that y is our number of scooters sold, x is our time. We can figure out at a specific year how many scooters they sold. That is a lot of work. So let's add those calculators. I'm going to show you on this app as far as I can show you, but it's going to break down pretty quickly because the app is old. So, part C wants us to use a graphic calculator to find the exponential model. We just found the exponential model, so it should be really close to that. Then we're going to predict the number of scooters sold in the 8th year using that model. So, in your calculator, really quick, Laura, I'm going to have to clear this. Okay, so I'm going to this. So take care of this one. First hour. Okay. So in your calculator, the third column, 3 buttons down, says stat. In blue, it says list above it. We're just going to use the stat button for today. So hit stat, then third column, third button down. It's under your Zoom button, 2 down. Once you're there, you see this thing that says edit. This is where we're allowed to edit our lists. So you hit enter once you're on edit, and you should see an L1, L2, L3, L4, L5. These are your lists. L1 is going to be our X, and L2 is going to be our Y. Now, the data that we're going to use, be careful, the data we're using is not the table that we made. So we're not using this table, we're using this table. You have to use the original one, okay? Do not use the one that we made. Because we want to exponentiate that original data. We want to find that exponential model. So, my L1, this is your X's, so it's going to be 1, enter. 2, enter. 3, enter. 4, enter. 5, enter. 6, enter. 7, enter. These are just my X values in that first table. Once you have those, you can scroll to the right to our L2. For L2, it's going to be 12, 16, 25, 36. So 12, enter. 16, enter. 25, enter. 36, enter. 50, enter. 67, enter. 96, enter. The important thing here is that these lists have to be the same size. If they are different lengths, it's going to not work. Alright, here's where my app ceases to be helpful. So once you have these lists entered, hit second quit so that you're on the main screen. Now you're going to hit stat again, but now you're going to scroll one over to the right to where it says calc. Alright, now the app is not useful. What you should see is you should see a whole big list, and I believe it's option 0. Scroll down to option 0. And it says EXP REG. That's your exponential regression. That's what we're doing. We're making an exponential function. So you're going to scroll down to that and hit enter. Now again, different calculators are going to say different things. If you have an older calculator, it's just going to have EXP REG on your main screen, and you can say enter again.
Where do you go after you come to this thing?
So just stat again. And we'll calculate the whole thing. Go down to 0. Okay, so if you have an older calculator, it just says EXP REG and then in the looking box, hit enter again. If you have a whole menu of things, it says X list L1, Y list L2, frequency list, store, reg X, I don't know what that means, and calculate. You're going to scroll down to calculate. That one just lets you choose which lists you're using. But just scroll down to calculate and hit enter. Once you hit enter, what you should see is a Y equals A times B to the X. And then you have an A equals 8.46, B equals 1.42. Did anyone not get that? Good stuff. Okay, so on notability, that is our exponential. So the calculator gives you Y equals 8.46 times 1.42 raised to the X. That is darn close to what we got. Again, it's a little different depending on your points, but we got 8.41, they got 8.46, that's a difference of 0.05. So we were pretty close. You can efficiently use that to find your exponential model. Alright, so the rest of us wants to predict the number of scooters sold in the 8th year. Remember, X is our years. X is years. So you can just plug Y equals 8.46 times 1.42 raised to the 8th. You're going to get a decimal. Remember, we don't want parts of the scooter, so we'll round this to a whole number. And we'll say that Y is equal to about 140. So the answer for this one would be about 140 scooters sold in year 8. Any questions about that? My people over Zoom, I'm sorry I'm not there to help you with your calculators. If you have issues with it, let me know, and once you're back here physically, I'll walk you through it again.